Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Miller, and I'll be your host and presenter for today's webinar on identifying and mitigating RF interference for cell phones, aircraft carriers, and everything in between. Please use the Q&A feature to submit any questions you have during the webinar. At the end of the webinar, I will address any questions that you submitted. Some background information on myself. I am one of the owners here at EMA. My group at EMA provides analysis services for radio frequency interference, installed antenna performance, and radar signature prediction. I personally have over 26 years of experience in electromagnetics. My career started with the Boeing Company as an electromagnetic effects engineer back in the late 90s. Then I worked for SAIC Demico as a research scientist supporting the X-Patch, Urbana, A-Patch, and Ant Farm simulation products. In 2005, I co-founded Dell Cross Technologies, where I served as the president. Dell Cross developed commercial simulation products for RF interference, installed antenna performance, and radar signature prediction, including the EMIT and Savant SBR Plus products that are now part of the ANSYS portfolio. In 2015, we sold Dell Cross to ANSYS, and in 2017, I joined EMA. During my career, I've worked on many RFI analysis projects for military and commercial customers for air, space, land, and sea platforms. Without further delay, let's get started with the webinar. Okay, so the agenda for the webinar today, first is a very brief introduction to our company, Electromagnetic Applications. And then I want to share with you some success stories as motivation for why we do the RFI analysis that we're going to talk about in this presentation. We will then talk about installed antenna performance, because there is sometimes confusion about this part of the RFI problem. It's certainly an important part, but not the entire story. Then we'll dive into the full RFI problem, and I'll work through one example scenario to show you some of the typical problems that we run into with an RFI project and how we would go about mitigating those. And then we'll spend the last 10 to 15 minutes answering any questions that are submitted during the webinar today. Okay, so again, very briefly about our company. So EMA has been around for 47 years at this point. We got our start working on electromagnetic pulse problems back during the Cold War, and then over time we expanded into other technical areas, including lightning, HERF, EMI, EMC. More recently, we added capabilities like space radiation effects and radar signature capabilities, and most recently, we've added AI, ML capabilities to our team. As noted here, as it's circled, today we're going to be talking mostly about antenna performance and radio frequency interference, but I want you to be aware of these other capabilities that we have at EMA. Another important aspect of our company, so there are really three core parts to our company. We create simulation software products, so we are the developers of the ANSYS EMC Plus and ANSYS Charge Plus products that are distributed and supported by ANSYS. We also have measurement capabilities, so we can perform lightning testing, HERF testing, EMI, EMC testing, RF measurements, as well as space radiation effects. And then our consulting services is really a big part of what we do here at EMA. We are recognized subject matter experts in these various technical areas shown on the left. And so we work with companies around the globe, everything from military applications to automotive to renewable energy, and just about anything that includes electrical devices, cables, and antennas. That's a pretty good description of a typical customer for us. So that is a very high-level overview of who we are as a company. I think it's pretty unique that we do all three: simulation software, consulting, and measurements. There's a lot of synergy between those different parts of our business. Okay, so before we dive into all the details about RFI, you as a viewer, participant in this webinar, Why is this important? Well, it's important because finding RFI problems late in a design cycle can be very expensive to fix. Not always, but it often is. There can be embarrassment, publicly having to acknowledge that you fielded a system, whether it's consumer electronics or a military system, that had issues with it. And in extreme scenarios can result in loss of life. And unfortunately, that has occurred in the past. And of course, no one wants that to happen. So what we try to do with our approach here at EMA is we try to get involved early in the design cycle so that we can find these interference problems before they manifest themselves into real problems that are discovered. And then we have to go back and do a redesign, a recertification. Every time you have to go through that process, it represents, real cost to your program. So we want to find these problems early and mitigate them as cost effectively as possible. So that's our motivation for solving RFI problems. So I want to share some success stories with you. Again, at EMA, we work with a wide variety of customers. When I started my career, when we talked about COSITE or RFI problems, it was almost entirely military problems. Fast forward to today, and that is not the case. Lots and lots of, well, virtually anybody that has two or more RF systems on their platform needs to be concerned about RFI problems. So some examples, we work with a lot of space launch and exploration companies and organizations. For example, we did some work for one customer, and we can't list customer names here because of confidentiality clauses, but we worked with a customer and they were integrating Iridium and Inmarsat systems onto a platform that also had GNSS receivers on board. And when we first did our RFI analysis for them, we went back to the customer and said, there's no problem, no interference. In fact, you've got 30 dB of margin, meaning any interfering signal is 30 dB below the susceptibility of that receiver. But then we got our hands on the actual GNSS receiver and we measured it. And then we plugged that data into our analysis. And we had to go back to them and say, not only do you have an interference problem, but it is a 30 dB. So a 60 dB swing from a 30 dB margin to a 30 dB interference problem. And that's the sort of thing none of us want to have to take to our boss or a customer and say, uh-oh, the spec sheet for this particular unit was not correct, and its actual performance is very different, and we have a real problem. And so for this customer, we were able to find that again in the design process, and we're able to avoid a potentially catastrophic issue with that scenario. We've also supported a lot of military organizations, so we've had the opportunity to measure military radios like the ARC 210 and the PRC 117G, the PRC 150. And what's always really interesting and kind of eye-opening is when you compare the measured performance with the performance stated on the LCID DD1494. And for those of you who are not familiar with that, a DD1494 is kind of like a military spec sheet. And so anytime that you're getting a military radio certified for use on a program, you have to go through this process of getting a DD1494. And so it's really interesting when you compare the measured performance with what's stated on the 1494. We have seen time and time again where they're off by 20, 30, 40 dB from what's stated on the 1494. So moving on, a couple more success stories. We've worked with autonomous delivery systems. As you can imagine, anything that is operating autonomously has to have a very, very high reliability rate. And so we characterize the RF systems that were going to go on this platform and use that data to identify some of the interference problems that would have occurred had we not found these issues early and then implemented some filters to mitigate them. We've also supported satellite manufacturers. We do quite a bit of work with these types of companies. As you can imagine, fixing an interference problem on a platform that is on orbit is not easy to do. Not impossible, but it sure is not easy. And so we've used our measurement system called ARMS, and I'll talk about that more later in the presentation. ARMS is Automated Radio Measurement System to characterize the RF systems that are going to go on some of these satellites, and again, try to find those interference problems early on. Okay, so when we talk about the RFI problem, there tends to be some confusion about what I call RFI, which is the full system from the transmitter to the receiver, and we'll get into more details about that here in a moment, versus what some people are really talking about when they say RFI is antenna to antenna coupling. And they're both important. Antenna to antenna coupling is a measure of how one antenna couples to another antenna. Typically, that's going to be your transmit antenna to a receive antenna. And so as part of this, we need to either measure or simulate the installed performance of these antennas to understand how the platform is changing that coupling between the various antennas on board. In this image on the right, I show a fighter airplane with some antennas, and you can see, the ripples and the distortion and the radiation patterns for those antennas as mounted on the airplane. This is one example. Of course, if you're working on, say, a cell phone, it's in some ways different, but also very, very similar because in that situation, we're looking at coupling maybe between traces and antennas. If we're working on the desense problem. At the end of the day, we need coupling data that is going to tell us how the threat is coupling energy to the victim system. And so this is a very important part of that process. So in some cases, you can measure that coupling between the antennas. There are a lot of cases where it is either impossible or impractical to measure the wideband antenna to antenna coupling. And so we typically will use simulation to characterize the coupling between these antennas. So the approach we use here for the antenna to antenna coupling, the first thing that you need is a high fidelity or highly accurate model of the antenna. As you're going to hear in a moment, this is a wideband problem. So we're not just interested in the narrow band or the intended performance frequency band of the antenna. We want to know also about the out of band performance of these antennas. And so there really are two basic ways that you can approach this. One is if all you have is the spec sheet for the antenna, you can reverse engineer the antenna and come up with an electrically representative model of that antenna. And we do a lot of that here at EMA, and we've had a lot of success with it. Does take some, optimization in the simulation tools and trial and error and things like that. But we've generally been able to produce very accurate models for antennas by reverse engineering them from the spec sheet. So that's one way to approach it. The other way to approach it is some of the antenna vendors, and it's actually really encouraging to see more and more of this happening in the past 5 years or so. They are providing what are called black box or component models for their antennas. And so what's nice about that is it is the full model for the antenna that the vendor created when they were designing it. It includes the matching networks, the material properties, specific geometry, and all the nitty-gritty details that you really want about that antenna. But as a consumer of that model, all we see is the outer mold line for the antenna. We don't get to see the details, but we've got a model that faithfully represents that antenna. And then we can take that model and place it on our platform and use it to compute the installed antenna to antenna coupling. So those are generally the two different approaches that we take. In the presentation today, I'm going to show you some examples of the component models that Dayton Granger has shared with us for some of their antennas. And when you can get your hands on those types of models, it's really a big time saver, but it's also a confidence booster that you know you're using the right model for the antenna. Okay, so the key takeaway from this first section on antennas is that The installed performance is certainly important. We need to know that antenna to antenna coupling. We need to know it in a wide band sense. So it's not just the narrow band performance of the antenna, but it's also below that and above it, because typically you're going to have systems that are operating below and above the design frequency for a specific antenna. Okay, so now let's get into more of the RFI problem. So, kind of in a nutshell, the RFI problem is we've got multiple transmitters that are located on a platform, and they are coupling to a victim system on that same platform. Again, I'm showing a fighter airplane here. If your application is a consumer electronics device, a car, a ship, whatever it may be, yes, there are nuances about differences in the platforms and maybe some special considerations. But at the end of the day, you need to know how the threat is going to couple to the victim system. And you need to know the in-band and out-of-band performance of your RF systems. And that's exactly what's being illustrated here. So these blue traces are showing the fundamental of the transmitter, and then you see some harmonics of those transmitters. You see some spurious emissions, and those are all coupling via the antenna to antenna coupling to the victim system. And that victim system has the intended channel, which is this deep null here. And then you've got some spurious responses of the receiver. And so we have to know how all these different systems are coupling to the victim and the victim's wideband frequency response. So it gets complicated pretty quickly. In the example I'm going to show you today, we're going to look at a single transmitter to a single receiver to reduce the complexity of the problem. But it's very common when we're working on these types of problems to have tens of transmitters and receivers, and each transmitter and receiver can have hundreds, thousands, tens of thousands of channels that they support per transmitter and receiver. So we've had scenarios where we've had to consider over 1 billion transmit to receive channel combinations. And then at that point, you have to be very smart and judicious about how you analyze those results to make sense of them. But again, today we're gonna focus on a much simpler problem. Okay, so what our customers typically want to know, we start at the highest level. Are there problems? Okay, so that's the first one. And then if the answer is yes, that there are RFI problems, what are the specific channels on which we experience interference? I just said a moment ago, a lot of times we have situations with radios that support many different channels. Okay, oftentimes what we'll see is it's just a very small percentage of those channels that are actually experiencing interference or causing interference to happen. And so sometimes the very simple answer is just frequency planning. It's okay, don't use this combination of channels when you're receiving on this other combination of channels. And that is a very cost-effective way to address that problem if you have that flexibility. Sometimes you don't. So if you do have an interference problem that you cannot avoid via frequency planning, then the first thing you want to know is what's the magnitude of the interference. How I go about solving a 3 dB interference problem may be very different from how I solve a 30 dB interference problem. So I need to know the magnitude of the interference and what's the root cause? Is it a harmonic of the transmitter? Is it a spurious response of my receiver? You need to know the root cause of the interference. And again, we're going to show you some examples of that today. So once you know those things, now we can start talking about how do we mitigate the problem. It's To be honest with you, it's pretty rare that we have the luxury to move the antennas. Sometimes we do, and sometimes you can move, say you've got two antennas on top of a platform, you can put one on top, one on the bottom, and maybe that gets you enough additional isolation to make the problem go away. But to be honest with you, most of the times when I work on these types of problems, the antenna positions are fixed or mostly fixed. So then you have to look at things like, can we use frequency planning? A lot of times we'll use filters. So we may use low pass, band reject filters to mitigate specific problems. Sometimes the interference is due to clock signals. And so we can try changing the type of clock or the frequency of the clock to mitigate the interference. Um, Honestly, sometimes the RF system is the root cause. Yeah, if you've got an RF system that is not meeting performance specifications, with our arms measurement system, we can measure it, and if it's not meeting the spec, you as the customer can go back to the vendor and say, "Hey, look, we measured it. It doesn't meet spec. You need to fix your RF system," or you move on to another vendor that has better performance. So there are a lot of different options for how we mitigate the problem, and it really comes down to the magnitude of the interference and the type of interference, again, whether it's in band or out of band. Okay, at the very most basic level, there's two types of interference. There's in-band and out-of-band, and I like to illustrate those with this simple, almost cartoonish example on the right here. So the red trace that you see is the transmitter wideband spectral profile. So here's the fundamental at 100 megahertz, and then we've got harmonics at 200, 300, and 400 megahertz. And then the receiver spectral profile is this blue trace. And so we have the in-band performance of the receiver at 200 megahertz. And then we've got these spurious responses that are happening at seemingly random frequencies out of band. So when we say in-band interference, it's any signal from the transmitter that's falling in the passband of the receiver. So in this example, it's the second harmonic of the transmitter that's falling in the passband of the receiver. An out-of-band interference problem is when any signal from the transmitter falls in an out-of-band response of the receiver. So in this example, it's the fundamental falling in the spurious response of the receiver. Okay, so you may look at this and say, well, that second harmonic problem, that's really obvious. That'd be an easy one to fix. And that's true, but the challenge is sometimes we'll see interference problems where we have both in-band and out-of-band interference occurring simultaneously. And so we'll have some signals falling in the passband of the receiver, but then we also have signals that are falling in spurious responses. And so you go in and you try to apply the easy solution, which in this case would be a low pass filter on your transmitter to knock down that second harmonic that's falling in the passband of the receiver. And you think you've got the problem solved, and you go retest and you still have interference. And it's because you didn't know about the spurious response of the receiver. So the point here is these can be pretty complicated. They very often are not trivial things to figure out and mitigate if you're not using simulation coupled with measured data. Okay, so what's important to model, and not trying to be silly here, but it's really everything, right? It's every piece of the RF architecture on the transmit and receive side, as well as the antenna to antenna coupling. We need high fidelity wideband data for each piece of the architecture and the coupling. So the good news for antenna to antenna coupling is that we can often measure this or simulate it and get very high fidelity results. Same thing goes for things like filters and cables. You can go to your laboratory and hook up a vector network analyzer and pretty quickly get high quality S parameter data for those components. But the question or the hard part is really, where do you get the high fidelity data for the transmitter or the receiver? And that's where we can use, again, the measurement system that we have here at EMA. It's called ARMS. We can measure the wideband emissions, and we can measure the wideband susceptibility of these RF systems, and then plug it into a simulation tool. In this example, I'm using the ANSYS EMIT software, which was originally developed at Dell Cross, but it's now part of ANSYS. And this is really a great tool for performing this sort of RFI analysis in it. Okay, so at this point, I want to get into a very specific example. Again, I'm showing an Apache helicopter here, If you're not in the military domain, it's okay. The same ideas that we're going to describe here are applicable to a lot of different types of problems. So if you work in consumer electronics, just imagine that this is a phone or some other sort of electronic device. At the end of the day, there's a lot of similar approaches and types of data that we need regardless of the type of platform that we're considering. So in this example, we've got a VHF, UHF transmitter, and we're going to show that it causes interference to a GPS receiver, and that interference is due to harmonics of the transmitter falling in the passband of the GPS receiver. We're going to use some vendor models for GPS and UHF antennas. These are going to be those black box or component models that I talked about earlier. And we're going to use models for typical UHF transmitter and GPS receiver. We're going to demonstrate that there's interference between the transmitter and receiver. We'll try to mitigate that interference with an initial filter and show that actually the filter doesn't do what we expect it to do. And then we'll finally mitigate it with an appropriate filter and show how we can make that interference problem go away. Okay, so first of all, like we talked about earlier, the first thing that we have to do is to model the antenna performance. In this case, we're going to use some Dayton Granger antennas. Dayton Granger makes a variety of products, including antennas, and they provide HFSS component models for their antennas, which is a really nice thing. If you're a user, so you don't have to go in and reverse engineer those antennas, you can just get them directly from Dayton Granger, and you have high quality models that you can use for your simulation. So in this case, we've got their VUHF blade antenna and their GPS antenna that we'll use for this analysis. So first we show the Dayton Granger GPS antenna. We've mounted it on top of the stabilizer at the back of the Apache helicopter, and we computed the installed radiation pattern for that antenna. So you can see ripples in the pattern. Of course, if this antenna were mounted on like a flat ground plane, finite size ground plane, it'd be a very smooth, slowly varying radiation pattern. But as soon as we mount it on a realistic platform like this Apache, we get interactions with the platform, and it introduces all these perturbations or ripple in the radiation pattern. And to look at that in a two-dimensional sense, we can look at a single cut here where the red trace is the free space performance of the antenna. And again, as I just said a moment ago, it's very slowly, smoothly varying. But then when we mount it on the platform, we get much more variability in the radiation pattern. Okay, the second antenna is going to be this VUHF blade antenna, which is going to get mounted on the bottom of the structure on the back of the Blackhawk. So it's a 6.5-inch top loaded antenna. And again, if we look at the free space versus installed performance of the antenna, we can see some significant variations in the performance, on the order of 5 dB or so. Sometimes the free space performance outperforms the installed performance, and sometimes vice versa, where the installed performance is actually higher gain than the free space performance. So we use those antennas to compute the wideband coupling. And again, this is being performed in HFSS. And you can see how that coupling varies as a function of frequency from 200 megahertz all the way up to 1.8 gigahertz. And I've zoomed in right at L1, which is 1575.42 megahertz. And we can see that we're getting about 73 dB of isolation between the transmit and receive antenna. And so, just off the cuff, this seems like that's pretty good isolation. 73 dB of isolation is quite a lot between a transmitter and receiver. And so if you were to just look at isolation, you might walk away with a false sense of confidence that I'm not going to have an interference problem here. But as we're going to show in a moment, you actually do have an interference problem because of other factors. Okay, so let's dig into the RF architecture. So on the left-hand side, we've got our transmitter. It is going to operate from 390 megahertz to 400 megahertz and 50 kilohertz steps. We are transmitting 50 watts or 47 dBm out of this radio, and it's connected to that VUHF top-loaded blade antenna that we showed on the previous slide. We are going to assume the harmonics follow the mil standard 461 requirements, and that's what is depicted in this image on the lower left. So we've got our second and third harmonics down at negative 20 dBm, sorry, and then our fourth and subsequent higher harmonics are at a lower level according to the mil standard requirements. On the right-hand side, we've got our GPS architecture, and this is very common on a GPS receiver. There's typically a front-end filter, a bandpass filter, and then you've got an amplifier because the GPS signal is typically a very weak signal, so we need to boost it before it goes into the GPS receiver. And so that amplifier is providing 37 dB of gain at L1. And our filter is providing 40 dB of insertion loss below 1.5 gigahertz and above 1.65 gigahertz. And then you can see the roll off. So we basically have 0 insertion loss in the pass band, a roll off region, and then 40 dB above and below that band pass region. And then what is depicted on the right here is our receiver susceptibility. So here is our in-band response. Now up top here it says sensitivity of negative 134 dBm, and that is accurate. What we're showing down here is the susceptibility. And so the way that the reason that there's a difference between the sensitivity value and the susceptibility is that we're accounting for the processing gain of the receiver. And this is associated with the spread spectrum technique used in this GPS architecture. So the actual susceptibility is not negative 134 dBm, it's more like negative 104 dBm. And then you can see the selectivity profile, which is basically how that susceptibility rolls off as a function of frequency. And so this is characterizing our receiver's performance. Okay, so we ran the simulation again in the ANSYS emit software, and we're predicting a lot of interference problems, 61 total, due to the fourth harmonics of the transmitter when it's operating over these channels from 392.45 megahertz to 395.45 megahertz. And it may be a bit of an eye chart, but I show all the specific frequencies here. And you can see how the amplitude of the interference varies. The lowest interference level is 1.6 dB, meaning that that interfering signal is just barely above the susceptibility of the receiver. And that's because it's probably in the skirt region on the, the selectivity profile for that receiver. And then as the harmonic falls closer and closer to the center frequency of that receiver, it increases in amplitude all the way up to 34.2 dB. And that's a pretty sizable interference problem, 34.2 dB. And so that is definitely something that we need to be concerned about. So let's dig into this and try to understand what's going on here and how we should go about mitigating this. So a really nice feature about the emit software is that you're able to look at the spectral profile of the transmitter emissions at any point through this architecture. And so we're going to start out first looking at the spectral profile right after the transmitter. And so what we see below here is the red trace. This is what's coming out of our transmitter. So here we've got our fundamental up at 47 dBm. We've got our second and third harmonics, our fourth harmonic, and subsequent harmonics. The blue trace is the receiver susceptibility. And so what you see at this point is that the magnitude of this fourth harmonic is significantly higher than the susceptibility of the GPS receiver. However, that is over here, and what we're really interested in is what's going into the front end of the receiver. So as we noted earlier, we're getting about 73 dB of isolation between the transmit and receive antennas. So when we account for that, that knocks that fourth harmonic down below the N-band susceptibility of this receiver. And so if we just stopped right there, we could say no interference problem. We're below that susceptibility threshold. However, that's not the end of the story. We have other components that we have to consider here. So we go through the bandpass filter, and as you may have noticed there, I'll go back and forth. Uh, that bandpass filter is knocking down these harmonics by about 40 dB, but it's not touching this fourth harmonic, right? The insertion loss at that frequency is effectively zero. So that fourth harmonic flies through that bandpass filter, and then it hits this LNA. And now it's getting boosted by 37 dB, and now we are back up above the susceptibility of this receiver. And this is the signal that's going to go into, this is a signal that's going to go into the receiver front end. Okay, so that's, if I go back a slide here, this red trace is the amplitude of the signal going into the receiver front end. What we talk about in terms of interference is the EMI margin. Anytime the margin is a positive value, that means that your interfering signal is above the susceptibility of the receiver at that frequency. So in this case, we have an EMI margin of 34.2 dB. That means the received power level was 34.2 dB above the susceptibility of the receiver. Again, that is a significant problem. That is something that you need to be concerned about and try to find a way to mitigate that interference. Okay, so what do? Well, a very logical response here is let's throw a low pass filter after our transmitter, because that low pass filter's not going to significantly impact your transmitter fundamentals, but it should attenuate those harmonics and any other unwanted signals, right? And so that's not a bad idea. The detail here that's really important is that you have to make sure that you understand the wideband performance of that low pass filter. So what I'm showing here is measured data for a low pass filter, and the spec sheet for this low pass filter said that we're going to get 50 dB of insertion loss. Okay, well, when we actually measure it, we see that we do get that 50 dB of insertion loss up to about 1 gigahertz. But then above 1 gigahertz, we start to see that performance degrades. And by the time we get out to L1, which is roughly somewhere out here, we're only getting about 30 dB of insertion loss. So there's 20 dB that we're not, the spec sheet said 50, we're actually getting 30. And so that's important, and that can be really significant, and we're going to show in this case it really is. So when we throw that low pass filter on the front of the transmitter, we do indeed see that EMI margin drop significantly. It used to be 34.2 dB, and now it's down to 3 dB. But we still have interference, okay? And so what we need to do at this point is to find a better filter. And so in this example, we're showing a Dayton Granger filter. And as you can see here, that's the blue trace versus the original filter we looked at, which is the black trace. And so we're getting much better performance out here at 1.575 gigahertz, somewhere on the order of about 70 dB of insertion loss. So really good performance out there. And if we replace that low pass filter with a Dayton Granger filter, now we see the interference problem goes away. Again, keep in mind EMI margin. If it's negative, that means the interfering signal is below the receiver susceptibility. So the closest it comes to causing interference is 31 dB below the GPS receiver susceptibility. So we have effectively resolved the interference problem at this point. Okay, I'm going to wrap up my slides here in just a moment, but I want to just talk briefly about our ARMS capability in a bit more detail. So ARMS was funded by a Navy SBIR, small business contract. Again, the Navy, like a lot of organizations, they face co-site interference or RFI problems, and they have this same problem that everybody else faces. It's garbage in, garbage out. If you don't have a good model for your transmitter and receivers real world performance, you're not going to get the right answer. I don't care how good the other parts of the problem are in terms of, I've got really high fidelity antenna to antenna coupling data, high fidelity filter data, cable data, etc. You're getting a lot of it right, but if you don't have the transmitter and receiver correct, you're not going to get the right answer. And so with our ARM system, what we can do is we can hook up to the transmitter or receiver, and we can measure the wideband performance so we know precisely what those harmonic amplitudes are and the spurious emissions and the out-of-band spurious responses of the receiver. So here are two examples. On the left-hand side is a UHF transmitter. The red trace is what we measured. The black trace is what the spec sheet said. You can see how far off some of those harmonics are, as much as 50 dB off. What's probably more troubling to me when I look at something like this is that there are a bunch of spurious emissions, and they're hard to see in this plot, but they're close to the fundamental. And those spurious emissions may only be down, 50, 60 dB from the fundamental. And since they're very close to the fundamental, if you've got a filter on the front end of your transmitter, they're going to go straight through that filter. And it's very common on some of the platforms that we work on where there are multiple UHF, VHF transmitters and receivers. And so even if those transmitters and receivers are operating on different channels, those spurious emissions, while they seem like they're low in amplitude, they can cause interference to those receivers, especially when your antennas are relatively close to each other. So there's a lot of really important data that we can provide in terms of the transmitter performance. Same thing on the receive side. If you look at this GNSS receiver, here we're looking at L1. Look how much wider the selectivity profile is for this receiver compared to what the spec sheet said. And then we also have this out-of-band spurious response. This is not the L2 frequency. This is just a random frequency. This is like 1.28, 1.29 gigahertz. And if I inject a signal above negative 20 dBm at this frequency, I will see the carrier to noise ratio for this GPS receiver start to degrade, and eventually I can jam this GPS receiver out of band. So this opens up some really interesting discussions around like stealthy ways to jam receivers without seeming like you're trying to jam those receivers. Okay, so in summary, I want to leave plenty of time here for questions. By the way, if you haven't already, please submit your questions through the Q&A feature in the user interface there. So we can help you avoid these interference problems. And it is a combination of using the right simulation tools, using high fidelity measured data. Some of that measured data can come from, again, a vector network analyzer. It can come from our ARM system or potentially other sources. But you want to have confidence in the data that you're using for your analysis, or again, it's garbage in, garbage out. The earlier that you can get us or your team, I mean, if you do this in-house, that's fine. You want to start your RFI analysis early in the design process, the early design stages, because that's when you can find those interference problems and you can come up with the most cost-effective way to mitigate those interference problems. And then finally here, and not to repeat myself too much, but you really got to think about this in a wide band sense. Okay, these are not narrow band problems. You've got to look at the unintended frequencies. How is your system performing, your component? If it's a filter, if it's a cable, if it's a transmitter receiver, you need to think about not just the intended performance, but also the unintended performance of that particular device. So please reach out to me. I show my email there. It's very simple, matt@ema3d.com. Again, we provide consulting services. We provide measurement services. We work with a wide variety of military and commercial customers. So we'd be happy to help you on your project. So having said that, let's dive into the Q&A session. And let me open up that interface on the webinar here. Okay, so first question that we have, why do we need to perform this type of RFI analysis when all of the RF systems on our aircraft already have to meet MIL standard 461 requirements? Okay, that's a great question, and we get this one quite a bit actually. So this person is probably working on a military aircraft of some sort. So if you look in the appendix of Mill Standard 461 or Mill Standard 464, they'll actually talk about co-site. And what they're going to tell you there is that the requirements described in 461, 464 are basically guidelines. Okay, they cannot anticipate every combination of RF system that one might want to integrate onto a platform, right? So what they're trying to give you are basic guidelines, rules of thumb. If you follow, you're going to have to meet these requirements, but they don't guarantee that when I integrate all these different RF systems, some really high power transmitters sitting literally a couple of feet away from some very sensitive receiver, that they're going to be compatible. Okay, you just don't know that until you go and you characterize all of the components in the RF systems like we showed in the presentation today. It's only then that you truly know if you're going to have compatibility at the system level. Okay, next question. Can you model intermodulation products with your simulation approach? I talked about this briefly early on, and the answer is yes. So within the emit software in particular, there is a nonlinear device model, and you can specify parameters like the third order intercept point, the 1 dB compression point, and a number of other parameters that are used to define a nonlinear model for a mixer or an amplifier or devices like that. And then the emit tool will compute those intermodulation products for you based upon the RF signals that are present at that device and those parameters that you've specified. If you want to know more details about that, you can either reach out to ANSYS and ask them. I'm sure they can provide you with documentation on their intermodulation product model, or you can reach out to me directly and we can talk about it as well. Okay, another question. Do you ever consider interference between multiple vehicles? For example, multiple cars on a road or aircraft landing at an airport or on an, I'm assuming they mean aircraft carrier. Yeah, that's a great question. So, when I started my career back in the late 90s, it was almost entirely focused on a single platform. And for me, that was like an aircraft or a rocket or something like that. But if you fast forward to today, and like I showed an image in this presentation early on, a bunch of cars out on the interstate, and you've got in a typical car today, you've got GPS, you've got Wi-Fi, communication systems, you've got ADAS systems, and on and on and on, right? Bluetooth. And so what used to be like a single vehicle or single platform type of analysis, today we have to consider other vehicles that are nearby. The eVTOL problem is an interesting one because those eVTOL platforms are going to be flying through areas where they may be subject to radiation from a cell phone tower or a radar system or myriad of other RF systems in that environment, and they have to be able to operate there without interference. And so, yeah, that's a great example of where it's not just that, co-site is important. Co-site means just the RF systems on the platform. At EMA, we use the term RFI because it's more generic than that. It's more general. The RF systems don't have to be on the same platform. And I think as we, looked in the next couple of decades, those types of problems are going to be increasingly more complex and more common. And so, yeah, we can definitely address those types of problems. Okay, let's just hold on another minute or so here and see if any other questions are submitted online. I think I've addressed everything that's came in so far. But if you've got a question you want to pose, again, certainly email me directly at matt@ema3d.com. I am going to email out a copy of this recording so that you can review it in the future, share it with your colleagues. Okay, so I don't see any other questions coming in, so why don't we just wrap up. As a reminder, You'll be receiving an email from us with a link to the recording of this presentation. Again, feel free to reach out to me or through the ema3d.com website if you have any questions or needs. Next up in the EMA Solving Electromagnetic Challenges webinar series is 3D plasma simulations for plasma enhanced chemical vapor deposition, or PEC-VD, sputtering, etching, and more in ANSYS Charge Plus. And that is scheduled for October 30th. So we hope you can join that one as well. Thank you very much for your time today.